This video is about understanding the concept of friction and limiting or maximum friction. We need to be able to solve problems involving limiting frictions, including scenarios with connected particles. So friction is a force between two surfaces that are sliding or trying to slide across each other. For example, when you try to push a book along the floor, friction makes this difficult. Friction always works in the opposite direction to the direction in which the object is moving or trying to move. Friction is always slows the moving object down. The amount of friction depends on the materials from which the two surfaces are made. Friction always acts parallel to the surface. Okay, so let's do an experiment together. So place a book on the table. So it's just sitting there. Is friction acting on the book? No. Apply a horizontal force, but not enough to move the book. Is friction acting? What is the magnitude? So yes, because you're trying to move it, but it's not moving, because you've applied a horizontal force, yes, there is friction acting on it, and it is the same as the horizontal force because it's not moving. So it must be balanced. Apply a horizontal force, but now up to the point that you feel the book is about to move. Is friction acting? What is the magnitude? Again, it's just before the point where it's about to move, so friction is still acting, and it's still same as the horizontal force. Even though you increased it, it's increased as well. The friction has increased the same value. Apply horizontal friction that is only marginally bigger than the force before. Is friction acting? What is the magnitude? So yes, it is acting, but obviously friction has reached a maximum because now it's starting to move. So it's bigger than the force, so its friction has a maximum value that has been overcome now. What can we now say about the value of friction in the situation when the book was about to move? Friction was acting at its maximum. How can I increase this maximum value of friction? So we can either increase it one of two ways. So we can either change the surfaces involved, or we can increase the normal reaction force by increasing the weight. So if we put a heavier book, for example, then the maximum friction will increase. Okay, friction versus Fmax. Let's go through that now. So obviously some surfaces are rougher than others and will therefore produce greater frictional force. The coefficient of friction for a surface, usually denoted by mu, gives a measure of the roughness of the surface. A smooth surface has coefficient of friction equal to 0. A heavier object also results in a greater frictional force. In fact, the frictional force depends not on the weight of the object, but on the normal reaction R between the object and the surface. The frictional force F is given by F is less than or equal to mu times R. The special case F is equal to mu times R can only be used when a particle is about to move or is moving. Can only be used when it is in limiting equilibrium. The frictional force is exactly what it must be in order to prevent motion between the two objects. However, there is a threshold value for friction above which motion would commence. This maximum force is known as Fmax. So threshold value for friction above which motion would commence is called the maximum F max. Once motion has commenced, friction will always act at its maximum, is trying to maximum to slow the object down. So what we do know is we have F is less than or equal to mu times R, where mu is equal to the coefficient of friction, which is decided by the surface involved. F is equal to friction. R is equal to normal reaction force. And we have F max is when it is equal to maximum friction, which is equal to mu times R. F max is equal to maximum friction. So that happens when obviously the particle is in limiting equilibrium. So this is everything that you need to know. Okay, so if we've got a diagram here, as x increases, there will come a point at which the object is about to move. This situation is called limiting equilibrium. So when the object is about to move, friction at this point is called the maximum friction and is denoted F max. I place the book on the table and apply a horizontal force that creates motion. I then place a weight on top of the book. The object is now harder to move as the maximum value of friction has increased. F max is directly proportional to the reaction force of the surface on the object and is governed by the equation F max is equal to mu times R. Mu is a constant and is called the coefficient of friction. So it's just reiterating what we just said before, which is the two equations here. Okay, so let's answer some questions now using this theory. So a block of mass 5 kg lies at rest on a rough horizontal table. So we've got a rough horizontal table. We've got a block of 5 kg, which means weight is 5g. Reaction here. The coefficient of friction between the block and the ground is 0.4. So mu is equal to 0.4. So the friction will be mu times R. So it's going to be 0.4 R. Our horizontal force F is applied to the block. So F going this way. Find the magnitude of the friction acting on the block and the acceleration of the block when the magnitude of F is 10. So we've got acceleration here. Okay, so if we apply Newton's second law vertically, then we do get R is equal to 5g, which implies R is equal to 49 newtons. Then F max, so the maximum value the friction can take is mu times R, which is equal to 0.4 times 49, which is equal to 19.6 newtons. Okay, so A. When F is equal to 10 newtons, because F max is equal to 19.6 newtons, so to reach limiting equilibrium, the friction needs to be at 19.6 newtons, but it's obviously not, which means the friction will be the same. The object won't be moving, so friction will be the same, which is 10 newtons, and acceleration will be equal to 0. B, when F, the forward horizontal force is equal to 19.6 newtons, then friction, because maximum friction is 19.6, then the friction will also be 19.6 newtons. Again, it has reached limiting equilibrium, but it's not moving, so acceleration will be equal to 0. When F is equal to 30 newtons, because the F max is equal to 19.6 newtons, friction will be at the highest value, which is 19.6 newtons, which means if we apply Newton's second law horizontally, then we get F minus 0.4 R. So it's going to be F minus 0.4 R must be equal to mass, which is 5 times acceleration. Now F is, in this case, 30, minus 0.4 times R is 19.6, is equal to 5 times acceleration, which means acceleration will be equal to 30 minus 19.6 divided by 5, which means acceleration is equal to 2.08 meters per second squared. Okay, each of the following diagrams shows a body of mass 5 kg lying initially at rest on a rough horizontal ground. The coefficient of friction between the body and the ground is a seventh. In each diagram, R is the normal reaction of the ground on the body, F is the frictional force exerted on the body. Any other forces applied to the body are shown in the diagrams. In each case, I find the magnitude of F. 2. State whether the body will remain at rest or accelerate from rest along the ground. Part 3. Find where appropriate the magnitude of acceleration. So this is A. Okay, so we've got 5g here. So R will be, because it's obviously not moving vertically, R will be equal to 5g. So F will be equal to mu times R. So it's going to be a seventh times 5g. Okay, part 1. So F is equal to a seventh times 5g, which is a seventh times 5 times 9.8, which is equal to 7 newtons. Part 2. State whether the body will remain at rest or accelerate from rest along the ground. So because 12 is greater than 7, it implies because the forward horizontal force is greater than the resistance force, it will accelerate from rest. So now we need to find the value of acceleration. So that means Newton's second law applied horizontally. We have 12 minus 7 must be equal to 5 times acceleration, which means acceleration is equal to 12 minus 7 is 5. 5 divided by 5, which is equal to 1 meters per second squared. Okay, for the next one, we've got, if we apply Newton's second law vertically, then that means 5g plus 14 must be equal to R, since it's not moving vertically, which means R must be equal to 63 newtons. So we need that information first. R is equal to 63, so this is F will be equal to a seventh times 63, which is equal to 9 newtons. So F is equal to 9 newtons. So part 1, F is equal to a seventh times 63, which is equal to 9 newtons. Part 2, again 12 is greater than 9, which implies that it will accelerate from rest. So that means Newton's second law applied horizontally. We have 12 take away 9 must be equal to 5 times acceleration, which means A is equal to 12 take away 9 is 3, 3 divided by 5, which is equal to 0.6 meters per second squared. And the last example, so if we apply Newton's second law vertically to work out R, then we have R plus 14 is equal to 5g, which implies R is equal to 5g take away 14, which is equal to 49 take away 14, which is 35 newtons. So R is equal to 35. F will be equal to a seventh times 35, which is equal to 5. So part 1, F is equal to a seventh times 35, which is equal to 5 newtons. Part 2, because 6 is greater than 5, it will accelerate from rest. So it wouldn't have accelerated at all if they were equal, but in all these examples they are not equal. Part 3, then it will be 6 take away 5. So Newton's second law applied horizontally. 6 take over 5 must be equal to 5 times acceleration, which means A is equal to 6 take over 5 is 1 divided by 5, which is equal to 0.2 meters per second squared. Okay, next example. 2 particles P and Q of mass 5 kg and 3 kg respectively are connected by a light, inextensible, strong string. I should say string, I think. So we've got P and we've got Q. So P is 5g weight, Q has weight 3g. They both feel tension. Particle P is pulled horizontally by a force of 40 newtons. So 40 this way along the rough horizontal plane. The coefficient of friction between each particle and the plane is 0.2. So if this, because it's not moving vertically, then the reaction force is the same as the weight, which means the friction that Q feels is 0.2 times 3g, and P feels 0.2 times 5g. Okay, so A, find the acceleration. So it's obviously accelerating forward this way. Find the acceleration of each particle. So first thing what we need to know is we need to apply Newton's second law horizontally to whole system. Then we get 40 take away T, take away 0.2 times 5g, plus T take away 0.2 times 3g is equal to total mass, which is 8 times acceleration. So we've got that, and that cancels out. When you put 40 take away 0.2 times 5g, take away 0.2 times 3g, we end up getting 24.32 is equal to 8 times acceleration. So acceleration is 24.32 divided by 8. Acceleration is 3.04 meters per second squared. Find the tension in the string. So let's do Newton's second law applied horizontally to Q. Then we get T minus 0.2 times 3g will be equal to 3 times acceleration, which is 3.04. So T will be equal to 3 times 3.04 plus 0.2 times 3g, which means T is equal to 15 newtons. Explain how the modeling assumption that a string is light and inextensible have been used. So for part C, light means tension is the same throughout the length of the string. And it also means the mass of string is negligible. And inextensible means acceleration of masses is the same. Okay, in the system below, the coefficient of friction between the block and the table is 0.2. So we've got tension 1. So if we split it up, we're going to have tension 1 here. We've got 2g here. We've got tension 1 here. Tension 1 here. We've got 5g here. It's not moving vertically, so 5g here. We've got 0.2 times r, so 0.2 times 5g here. We've got T2 here, we've got T2 here, T2 here, T2 there, and 10g, the weight of the 10 kg mass. Now, because 10 kg is bigger than 2 kg, it's moving this way, the 5 kg is moving this way, and the 2 kg is moving up. So if we apply Newton's second law vertically on 2 kg mass, then we get, because it's moving up, we get T1 minus 2g must be equal to, so all these are, because they're all connected, acceleration is the same throughout, is equal to 2 times acceleration. So T1 is equal to 2a plus 2g. Newton's second law applied vertically on 10 kg mass. Then we get, because it's moving down, we get 10g minus T2 is equal to 10 times acceleration, which means T2 is equal to 10g minus 10a. Okay, Newton's second law applied horizontally on 5 kg mass. Then we have T2 take away T1. I made a mistake here. The arrow is pointing in the wrong direction. Remember, tension is a pulling force, so it's pulling it away. Okay, minus 0.2 times 5g must be equal to 5 times acceleration. But we know T2 is equal to, so T2 is equal to 10g minus 10a, minus T1 is equal to 2a plus 2g, minus 0.2 times 5g must be equal to 5a. So if we take all the a to the right hand side, we get 10a plus 2a plus 5a, which is equal to 17a. And if we simplify the 10g, take away 2g, take away 0.2 times 5g, we end up getting 68.6 here. So a is equal to 68.6 divided by 17, which works out to be 4.03529411, which implies a is equal to 4.0304 meters per second squared. Now we need to find T1 and T2. So remember, T1 is equal to 2a plus 2g, which means is equal to 2 times non-bounded version, which is 4.03529411 plus 2g. So T1 is equal to, when you put this into a calculator, you get 27.6705, which means T1 is equal to 27.7 newtons. T2 in a similar way is 10g minus 10a, which is equal to 10g take away 10 times the non-bounded version, 4.03529411, which gives us a value of 57.64705 blah blah blah, which is equal to 57.6 newtons. Okay, a box of mass 6 kg rests on a horizontal table and a coefficient of friction between the box and the table is 0.4. The box is connected by a light inextensible string passing over a smooth pulley at the edge of a table to a mass of 3 kg. So we've got a table, we've got a pulley, we've got mass here, and we've got mass here. Okay, so back 6 kg, so this is, the weight is 6g, rough horizontal. So this is a reaction force, which is going to be, because it's not moving vertically, is 6g. Okay, there's friction of 0.4 times 6g. So it's going to be 0.4 times 6g, the friction. Okay, there's tension here, tension here, tension here, tension there. And this is 3 kg, so the weight is 3g. And it's moving, accelerating down here, accelerating for us like there. Okay, 3 kg which hangs freely. If the system is released from rest, find the distance moved by the box in the first 3 seconds of the motion. You may assume that the box does not reach the pulley. So first thing we need to do is Newton's second law applied across for whole system. Then what I do know is 3g take away t plus t take away t plus t minus 0.4 times 6g must be equal to total mass, which is 9 kg times A. So everything, all the t's cancel out. And 3g minus 0.4 times 6g gives us 5.88. Must be equal to 9 acceleration. So acceleration will be equal to 5.88 divided by 9. So we get a fractional value of 49/75 meters per second squared. So now that we've worked out what acceleration is, we can set up a that equation. So we're trying to find the distance traveled. So distance is initially at rest. So rest means 0. We don't know the final velocity. We know acceleration is 49/75 and the time is 3 seconds. So we've got S, U, A, and T. So S is equal to UT plus half AT squared, which means it's 0 times 3 plus half times 49/75 times 3 squared, which means S is equal to 2.94 meters. A particle of mass mkg rests on a rough horizontal plane. The coefficient of friction is a third. The particle is connected by light and extensible string passing over a smooth pulley at the edge of a plane to a mass mkg which hangs vertically. So we've got a pulley, we've got a mass of m, big capital M, so it's going to be mg. It's not moving vertically, so mg here, and the friction applied here, which is going to be mu times mu, which is a third, times mg. Okay, obviously feels tension here, tension there, tension, tension. Okay, and this is m, lowercase m, so it's going to be mg. And it's find the condition the system should remain at rest. So if system remains at rest, then when we apply Newton's second law vertically, then to mass m, so the lowercase m, then we know T must, because it's not moving, T must be equal to m times g. So if we apply next Newton's second law horizontally to mass with capital M, then that means we might get T minus the friction must be equal to 0, which means the friction must be equal to the tension, which is just what we worked out is mg. So friction must be equal to m times g. Now if we apply Newton's second law vertically to mass capital M, then we get the reaction force. The reaction force is equal to capital M times G. We know friction must be less than equal to mu times R in all cases, which means we've got friction is equal to mg, must be less than equal to mu, which is a third, times R, which is capital Mg. Okay, so what we do know is if we divide by G, we get M is less than equal to a third M, capital M, which implies 3m. 3 little m must be less than equal to m. So that's the condition that the system should remain at rest. So m must be greater than equal to 3 times the lowercase m. Okay, the last question I go through. A train of mass mkg is traveling at 20 meters per second when it applies its brake, causing the wheels to lock. The train decelerates at a constant rate, coming to a stop in 30 seconds. By modeling the train as a particle, show that in this model the coefficient of friction between the railway and the track and the wheels of the train is mu is equal to 2/3g. So we've got a train. Okay, we know that it weighs mg. It's not obviously moving vertically, so the reaction force is also equal to mg. The frictional force must be equal to mu times mg, which is the reaction. It's accelerating forward. So first thing we need to do is work out obviously acceleration before we can do anything about finding mu. So if we set up a suvat, so we don't know how much it's traveled. We know the initial speed is 20. We know it comes to a rest eventually. Acceleration is what we're trying to find out. Time is 30 seconds. Okay, so we've got UVAT. So V is equal to U plus AT. 0 is equal to 20 plus A times 30. So A is equal to negative 20 over 30, which is equal to minus 2 over 3 meters per second squared. Okay, so now that we know that, if we apply Newton's second law horizontally, then we get negative mu times mg must be equal to mass times acceleration, which is minus 2 over 3. If both of them are negative, so we can change it to mu mg is equal to m times 2 over 3. We can cross out the m's, divide by m, whoops, undo, because m is non-zero. So we end up getting mu is equal to 2 over 3 divided by g, which is 2 over 3g, which is what we wanted. The train is no longer modeled as a particle, so the effects of air resistance can be taken into account. Okay, state with the reason whether the coefficient of friction between the track and the wheels will increase or decrease in this revised model. So now what we have is we have initial air resistance, which we label A. So for part B, A is greater than 0, because obviously air resistance will be pushing it back, so it means it must be greater than 0. So if we apply Newton's second law now horizontally, then we got negative mu times mg minus A must be equal to mass times acceleration, which is equal to minus 2 over 3. Okay, so if we change the sign of everything, then we get mu times mg plus A must be equal to m times 2 over 3, which means mu must be equal to 2m over 3, take away A over mg. So if I simplify that, mu will be equal to 2 over 3g for the first term, take away A over mg. Now this A over mg is greater than 0, therefore this whole thing must be less than, because we're subtracting a number that's greater than 0 from 2 over 3g, it must be less than 2 over 3g. Therefore, coefficient of friction decreases in the revised model.